Welcome to Wave Basics. Much of this is going to be review, but we also need to make sure our foundations are strong so that we can move further and learn a little bit more about waves and energy that is transported by waves. Waves are actually disturbances that transport energy, not matter. And we can talk about waves or pulses. A pulse is a single disturbance, whereas a wave is a repeating periodic disturbance. If you consider a slinky, look at the first diagram or the top diagram on your screen. If you imagine taking your hand and just sending it one pulse down the slinky or moving your hand one time, the pulse would travel through the slinky. However, if you moved your hand in a regular repeating motion over and over, you would create a wave or a regular periodic repeating periodic disturbance. There are two types of waves. We'll talk about electromagnetic, EM waves, and mechanical waves. The biggest difference in the two is particle motion and the fact that electromagnetic waves can travel through empty space, a vacuum, whereas mechanical must have a medium, cannot transfer through empty space. An example of an electromagnetic electromagnetic wave is visible light, and a mechanical wave is a sound wave. If you look at the two pictures at the bottom of the screen, I want you to look at these briefly, and then we'll discuss this a little bit more later. But particle motion on a transverse wave is perpendicular to the direction of energy in this picture. If you look to the right, particle motion, the vectors are drawn parallel to the direction of energy transport. That's real important to remember as we go through and discuss a little bit further. So keep that in mind. Transverse waves, as we said, were electromagnetic waves. And particles move or vibrate perpendicular to particle motion. If you look at the animation, now keep in mind this is just a one-directional motion animation, but if you look at one black dot, just focus on one dot, you'll notice that it is moving up and down. However, if you imagine for a minute the flashlight over to the left of your screen was turned on, the light would move to the right, or we would see the beam of light moving from the flashlight propagated to the right or horizontally, we could state for this diagram. However, the particle motion would be up and down or vertical. So the particle motion is at a right angle to or perpendicular to the direction of the energy propagation. This is a little easier to understand maybe if you look at the sketch just above the animation. You can see that the electromagnetic or transverse wave in this picture has both an electric field and a magnetic field that are moving at right angles to each other. So they would either be toward you or vertical, both of which would be perpendicular to the left to right direction of the wave motion, the wave energy movement. When we're actually drawing a transverse wave, there are many aspects of it, components that we need to consider, and as I said, some of this is going to be review. If you look at the top, you'll see wavelength labeled from one top of a crest to the next crest. And very frequently you'll see a textbook definition as wavelength is crest to crest of a wave. Wavelength is symbolized with the Greek letter lambda, and that's that little upside down Y that you see next to wavelength. We can also measure it in other areas on the wave. If you look at the point labeled node, the node is drawn along the red sine curve that you see, but it's also on that black horizontal line. And the horizontal line represents the equilibrium, or the rest position for that wave. Because that is at the rest position, the node is an area of no disturbance and no vibration. As you move outward to the top of the crest or the depth of a trough, those areas are known as antinodes, kind of the opposite of a node, and instead of having no disruption or no displacement, there is maximum vibration or maximum displacement. Once again, focus on the node, and if you travel on the sine curve, the red line down through the trough and up over the next crest and then stop just before you get to that vertical line labeled amplitude, starting and stopping at the equilibrium point, you will have also traversed or traveled one wavelength. because one wave consists of one crest and one trough, or in this we would have just traveled one trough and one crest. Be careful when viewing this picture, because if you look at amplitude, it looks like a rather long line from top to bottom. But hopefully you'll recall a vector is not going to point in two directions. So therefore that is actually two vectors. The amplitude is measured from the rest position to the top of the crest, or from the rest position to the bottom of the trough. So that line is actually two vectors, or a total of two amplitudes. Longitudinal waves, a little different than transverse waves. The particles are moving or vibrate parallel to the motion of the wave or the energy propagation. Once again, just looking at this on-screen view, we have both particle motion and energy propagation in the same direction, or parallel to each other. So the particle motion can be left or right, and the energy in this depiction or animation is to the right. If you look at that animation on the far left, you'll see the red bar moving. So consider that is the source of this longitudinal wave. That vibration is going to cause other molecules to vibrate. As you did before with the transverse animation, focus on one black dot. If you just look at one dot, you'll see, pick any one, that it's moving back and forth, left and right, not really going anywhere. However, if you kind of take a different approach and look at the picture as a whole, it appears as though there's this stream of particles that are moving from left to right. You'll see little vertical, almost lines of particles that are moving. And these are the compressions and rarefactions we'll talk about shortly that enable that sound to travel through the molecules without actual molecules moving from one location to another. So when we look at the aspects of a longitudinal wave, a little different than a transverse wave, we signify areas of compressions and rarefactions. Compressions are similar to crest, and those are those areas of the slinky where they're labeled A, C, and E, where all the little particles or pieces of wire that slinky are really tightly packed. So a compression is, think of what the word compression, to compress or to squeeze, and the particles are closely packed, and so those molecules that would be in that, or all of those, the metal of the slinky, would be under high pressure because they're all squeezed together. Conversely, the rarefaction, not refraction, not refraction, it actually is rarefaction, is an area where all the particles are kind of spread out. So B, D, and F on that same slinky, the pieces of the metal would be stretched or the particles would be stretched, and this would be representative of a trough on a transverse wave. Since the particles are all spread out, rather than the high pressure of the compression, the particles are under much lower pressure, so a low pressure region for the rarefaction. To measure a wavelength on a longitudinal wave, you would actually measure one compression and one rarefaction. So basically A and B would make up one wavelength, and C and D would make up another wavelength. The particle motion shown in the bottom drawing is more representative of the animation you saw on the prior slide. And those vertical lines that you could see kind of moving to the right as you watched that video were those compressions, and you can see it easily depicted here, whereas the spaces in between those vertical lines that appeared to be moving, even though the particles were just vibrating, were the rarefactions, or the regions of low pressure.